Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 11th, 2025, which was about 5 days ago. The striking result is that even a single-layer multi-head transformer can provably learn multi-step chain of thought reasoning through plane gradient descent by coordinating its heads to execute a sequential algorithm on tree path finding. The paper is titled, Multi-Head Transformers Provably Learn Symbolic Multi-Step Reasoning via Gradient Descent, and the implications for model training are quite significant. Beyond the proofs, the authors show head specialization, polynomial time convergence, and strong generalization to unseen trees, all emerging from an autoregressive training setup. Building on that, tweets highlight chain of thought as a learned scratchpad, enabling shallow transformers to run sequential algorithms, share the abstract and figures, and show moderate engagement around 119 and 28 likes. Alright, this illustration sets up the task. A small tree on the left, the textual prompt in the middle, and the required outputs on the right. The prompt lists edges as unordered pairs, plus the goal node 8 and the root node 4. Building on our earlier setup, the model must first climb from the goal to the root, yielding 8 to 1 to 2 to 4, then reverse that chain to produce the forward path, 4 to 2 to 1 to 8. Now focus on the three panels that map the whole story. Left shows the small tree, middle walks through backward steps, and bottom shows the two-stage forward process with a turning point. In the middle panel, each step highlights the current node and selects its parent, stacking outputs downward. In the bottom panel, stage 1 mirrors that backward sweep, then the stage token flips, and stage 2 streams the path in root to goal order. Next, the plot tracks loss over training epochs for the backward reasoning task, showing how learning stabilizes. Early on, both training and test loss sit near 2, then around 300 epochs, the training curve drops sharply, followed by the test curve with a slight delay. By roughly 600 epochs, both curves flatten near 0, indicating convergence and strong generalization. This aligns with the theory that the single attention head sharpens its focus, while off-diagonal interference remains small. Building on the loss curves, this plot zooms into the internal matrix H dynamics for backward reasoning. Focus on the graphic. The green curve tracks the diagonal entry H1, 1, which steadily rises from near 0 to about 5.5 as epochs progress, indicating sharpening self-alignment. Meanwhile, the red curve shows the off-diagonal entry H1, 2, which drifts slightly negative and stays close to 0, signaling minimal cross-interference. Together, these trajectories match the predicted mechanism of clean, concentrated attention. Moving to the parameter trajectories, this 6-panel figure tracks selected entries of the U and V matrices over epochs for forward reasoning. First, note the overall grid shows smooth, monotonic trends for most entries, with sharp changes early, then gradual saturation. In the right top panel, U3 shows the predicted pattern. U310 rises strongly, while U301 dips, then rebounds, reflecting role specialization. The bottom row mirrors this for V matrices, where V3 curves separate into increasing and decreasing branches, signaling stage control taking shape. Now we switch to the forward tasks learning curves. Focus on the main chart. The solid blue line shows training loss, and the dashed orange line shows test loss, both over epochs. Early on, training loss drops steeply to below 1 by roughly 2,000 epochs, while test loss decreases more gradually, crossing 3 around 3,000 and trending toward 1. This staggered, but consistent decline signals stable optimization and improving generalization as the two heads specialize into traversal and stage control. Continuing from those specialization curves, two takeaways stand out. First, even a single layer with two attention heads can learn a sequential algorithm, with one head traversing and the other controlling stages. Second, gradient descent naturally drives that division of labor and generalizes to unseen trees. Gradient descent means iterative parameter updates that minimize error. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.